So this is where your phi is between two constants, right? Your theta is between two constants, and your rho is between two constants. And that's what you get right there. So you get this three-dimensional patch. And so that is what a spherical box looks like. Do y'all see how everything's fixed between two constants? All right. So triple integrals. If our theta, phi, and rho are between constants, notice that these are not like functions, these are all constants. So this is the simplest form we could get with spherical. Then you have alpha to beta for theta, you got c to d on phi, you got a to b on rho. And then this is your function you're integrating, and then that's how you switch x over, right? That's what x is. This is what y is, and this is what z is. So here's your function of three variables. And then this part right here, this thing. So we know in cylindrical coordinates or in polar coordinates, we have to introduce this little r, right? That r always had to be there. Well, when you go into spherical coordinates, you have to throw this in there, rho squared sine phi. I'm going to explain where it comes from, but not here today. It will be next class. Because it's kind of strange that, with polar and cylindrical, you always have that r there. If we do this conversion, we go from Cartesian to spherical, we got to go throw this ugly thing in there. So it would be worth us talking about where that's coming from and why, right? Maybe? Okay. So let's do that question, this one right here in a second. I actually want to do something I think will be just as fun. I meant to bring up this. There we go. Show the volume of a sphere, of a ball with radius r, capital R, is 4/3 pi r cubed. And you're going to say to me, well, we already did that, right? We did that last class, didn't we? So why are we going to do this again? Well, the reason we're going to do it is because we're going to do it in spherical instead of cylindrical, which is what we did last class. So I'm going to be doing, since I'm trying to find the volume, I'm going to do a triple integral over E of 1 dV, right? I'm trying to find the volume of this thing. But I need to define the region E that I'm talking about, which is going to be this sphere of radius capital R, right? How can I draw that solid in spherical coordinates? So what is my phi going to have to go between? 0 and pi. So from straight up to straight down, right? And I'm going to be spinning around full rotation, 0 to 2 pi. Okay? And I'm going to let my rho, my radius, go between where and where?
0 and R.
0 and capital R. Do you all see that? Phi from 0 to pi, straight down. So all of these swung around like that, right? But my rho's between 0 and R, capital R. So I've got theta's between 0 and 2 pi. Phi is between 0 and pi. And rho is between 0 and capital R, because capital R is some fixed constant radius of my ball. And so now we just need to do this triple integral. So integral, integral, integral. We'll do our limits, or we'll do our limits of integration in the order here in a second. But what goes on the inside of this?
1 R.
1. But then we have to do that thing because we're in spherical. So rho squared sine phi, or phi. Okay, that has to go in there because we're in spherical. And then What are the things here? Does the order of integration matter? Look at our, they're all constants, aren't they? So this order doesn't matter at all. But I'll just go in the order that makes sense here, I guess. 0 to 2 pi, I'll go 0 pi, I'll go 0 capital R here. And then over here, that forces me to go d rho, d phi next, and d theta last. Right? Okay, let's do the first antiderivative. I think these are going to go pretty quick. Let's see. The antiderivative of rho squared sine phi with respect to rho would just be, yep, so 1/3 rho cubed sine phi, and we're evaluating that from where to where? From what equals 0? Rho equals 0 to rho equals capital R. D phi d theta. You understand what I'm doing here? Just integrating with respect to rho. Let's plug in capital R and then plug in 0 and subtract. And that'll be nice, won't it? 0, 2 pi, 0 pi. And when we plug in capital R for rho, we get 1/3 capital R cubed sine phi. And when we plug in 0 for rho, right, it just goes away. So now we're going to integrate that with respect to phi, or phi, or pho, it's up to you. Antiderivative of sine, of phi, negative cosine. So now we have integral 0 to pi. We have negative 1/3 capital R cubed cosine phi. We're evaluating from phi is 0 to pi. Okay, we have to do that, and then we're going to integrate with respect to theta. So what is cosine of pi? Negative 1, right? So when we plug in pi, we get negative 1, but it's already negative. So 0, 2 pi. Okay, we plug in 1, we get, when we plug in pi, we said we get 1/3 R cubed, right? Positive 1/3. And then when we plug in 0, be careful here, because what's cosine of 0? 1. So now we get minus a negative 1/3 R cubed. Is that all right? You understand what I'm doing there? And then just put that together. We still need to do with respect to theta. So what is that there? 2/3, right? 2/3 R cubed d theta is where we are. Antiderivative of that with respect to theta is 2/3 R cubed theta, right? And evaluate from theta is 0 to theta is 2 pi. And when you plug 2 pi in for theta, what do you get? 4/3 pi, right? R cubed. And when we plug in 0, it goes away. So you get. So on that, when we did it last class, we actually had to just look in the first octant and then multiply our answer by 8 at the end. Remember that? This one, we got the exact answer because we did the whole ball at one time. I'm not quite sure what took longer, but I think this is cleaner. There's a lot less room for error, I think, here. All right, let's do this problem now. So this is the triple integral. This is the function we're evaluating. And we're trying to integrate over this region E that's in the first octant in between the spheres with the radius of 4 and 9 respectively. What does that look like? You're in between two spheres, right? You have a sphere of radius 4, you're outside of that one, but inside the sphere of radius 9, but you are in the first octant only.
So, like a
Yeah, it's hard to describe. You mean that thing? Like that thing? Right? Did y'all see that? Is that what you were visualizing? Right? It's just like part of a coconut, I guess. So this region E, this solid, is a perfect spherical solid, isn't it? I mean, like it is just, we would not want to do this. I mean, could we do it with cylindrical? Could you?
yeah.
Ooh, this is a great question. Could you do this with cylindrical? Let's look at it from the top. Look at the shadow on the ground. Right? The shadow on the ground is actually the whole thing, isn't it? If we were trying to do this. But the problem is that it switches, like you have a change, like right here. Yeah, so if we look at it here, I don't know what the best viewing angle of this is going to be. I don't know how that looks on. Can you all kind of see that? If you're talking about above this piece right here, the bottom surface is that sphere, and the top surface is the other sphere. But when you go outside of this into here, the bottom surface is what? The XY plane, and the top surface is the bigger sphere. So you would actually have to break this into two different integrals to do it in cylindrical. That makes sense? But it's perfect for spherical. In spherical, all I need to come up are with some restrictions for these guys. And what would they be here? How can I draw that? So I'm over here in the corner of the room. So phi goes 0 to where? Pi over 2 would take me down to the XY plane, right? So everything between here and here, theta between 0 and just want to turn to the first octant. So 0 to pi over 2 again, right? So it's phi is 0 to pi over 2, theta is 0 to pi over 2. And then what about my rho? Yeah, I don't remember what the radius was. I gave you the radius as 4 and 9. Yeah. So this is going to be phi is between 0 and pi over 2. Theta is between 0 and pi over 2. Phi is between 4 and 9. So now we can set this thing up. Triple integral, we'll get the limits here in a second. Now I have to integrate e to the square root. Well, what do I do there?
Would you have to substitute the coordinate for the x, y?
Yeah, remember this thing from spherical. X squared plus y squared plus z squared is rho squared. So that's e to the square root of rho squared, which is just e to the rho. So this thing becomes e to the rho. And then I have rho squared sine phi d. Now I get to choose, because these are all constants again, right? So I get to choose the order in which I do these. And it really doesn't matter. So I'll stick to what I like to do. I always like to do theta on the outside. So I'm going to go theta on the outside, phi, and rho. Do we all understand this piece, right? That thing is going to be there every time you do spherical. The fact that becomes e to the rho, everyone's clear on that? I should mention, this is just something that might come up later in your life. I know a lot of times in math, when you're in class, we'll say that that's x, right? Right? But actually, technically, it's the square root of x. I mean, not square root, it's the absolute value of x. All right? So this should be absolute value of rho, but we know that the x, the y, and the z are all positives because we're in the first octant. So that's why we can just say rho. And we also know rho is positive, right? Like, isn't rho always positive? Spherical says it needs to be. Spherical, you always want your rho to be positive. All right, now, if I had to integrate that with respect to rho, ooh, okay. So sine phi is a constant. How would you integrate rho squared e to the rho?
By parts.
By parts twice, right? That would be like me asking you to integrate x squared e to the x dx. So you do integration by parts once, which would be able to take your x power down one time. Then you do it again, and it would get rid of your x on the new integral. So that would be an integration by parts twice. That would be the hardest part of that problem. Once you get past that, it's just going to be, you know, integrating sine, phi, and so I don't think I'm going to take you through that. Is that okay with you? I will tell you, however, what the answer is. You know what? Pardon me? Ooh. I don't remember what the problem was asking. Which one? The volume one or this one?
Wait, yeah.
Oh.
That's fine. The last one you couldn't. I always think of volume and not.
Yeah, on volume you could do this one pretty easily. If they were asking for the volume of this, right, coconut thing, it would be much easier to probably do with just the volume formula. But it's the fact that our function we're integrating is in there. What's going on here? Why is it giving me an error? Why is it giving me an error? Invalid integration variable or limits.
Maybe D row first.
It doesn't matter, actually. Oh, wait a minute. Did I get this? Oh, I have this backwards. But that shouldn't. Let me see. Yeah, no, because I'm calling it R. R is row for me, and P, I have no idea why I used P. Well, row? Yeah, maybe those are backwards. No, something is wrong. Let me try and run this one. That worked. No, there's something in that one. I don't know. Something's up with the answer should be this number right here. I've had the computer evaluate it before we came to class. So that should be it right there. 826,482. All right. So 3 problems for homework there. We've got about 20 minutes. I think maybe we'll just take 10 minutes. I want to start talking about 12.8 because it's a really complicated section. Do you have kind of a basic idea of, you know, cylindrical and spherical, you know, that what's going to dictate? Well, you tell me, what's going to dictate whether or not you want to use this versus this? The region, right? It's like, what does the region look like? If the region looks like something that is better suited for spherical, then you use spherical. Most of the time, you're going to have spheres involved, right? Then you know kind of do spherical. Okay, so I think the way I want to do this is I just want to show you this. I just want to give you the formula first. Okay? And then after I give you the formula, we'll talk about where it comes from. So I'm going to get to the notes here. Where are they? There we go. Yeah. All right. So we're talking about a double integral right now, not a triple integral, right? A double integral. Okay, so when we have double integrals, we usually have this region D, right? Two-dimensional region that we're integrating over. And what we kind of imagined is that this was a surface, right? And so this would give us like the volume underneath that surface down to the ground, right? That's what double integrals were. This says that if you'd like to make a change in your variables, like you want to move from x's and y's to something else, like maybe you want to switch your x's and y's to something with r's and thetas in it. So this right here, going from Cartesian to polar, is called a change in variables. We change from x's and y's to r's and thetas, right? This says that if you want to make a change of variables where your x is going to be some function of two new things. Now we've used r and theta here for polar, haven't we? And this would be like r and theta. Don't understand that? The x is going to switch to some function of r and theta, and the y is going to switch to some function of r and theta. But in general, it didn't have to be r and theta. It could be any change. Okay? Just in general, if you ever want to change from one variable, like a pair of variables, over to a different pair, then what you have to do is first, in your function, replace all of your x's and y's with the switch, which is what we did in polar, right? Everywhere we saw x and y, we switch it with r sine, or r cosine theta, r sine theta. So you got to make that switch within the function here. And then with polar, we had that little r, right, that popped out. This is what you have to do to determine what pops out. You have to take the partial derivative of x with respect to u. So here's your x function. You take derivative of this with respect to u, then multiply times the derivative of y with respect to v, and then subtract from it partial derivative of x with respect to v times the partial of y with respect to u. This right here, this piece, I'm going to try and convince you of where it comes from next class. Right now, let's just take it on faith. Can you just take it on faith just for right now? This piece right here, the absolute value of this thing, is called the Jacobian, or the Jacobian determinant. So what we have here is, just recap, you start off, let's say in Cartesian with x and y, integrating over some domain. You wind up switching over to some other variables, r and theta. Now what you're integrating over is no longer d, it's some other shape, maybe a polar region now, right? And you switch your function over, you do that little thing that computes to be r for polar, and then you change your with respect to variables. This is what we use to change variables for anything, all right? Polar is one example. So let's see how this formula works. I'm gonna leave this right here. Whoa. I'm just gonna leave that right up there. And I'd like for you to consider the following. I'm trying to do a double integral over d, f of x, y, dA. Try and do this double integral. And I'd like to make a change of variables. The change of variable I'd like to do is I'd like to replace x with u cosine v and y with u sine v. Look familiar? That's basically like r cosine theta, r sine theta, right? So this is basically, I'm going to make a polar conversion, just using different letters instead of r and theta, right? According to this, what I need to put in here, I have to calculate it. All right, so let's do this calculation. I need to take the partial derivative of x with respect to u. So here's my x function, right? If I asked you what the partial of that with respect to u is, what would you say?
Cosine V.
Just cosine v, right? Because u is the variable, cosine v is a constant, so derivative of this would just be cosine v. Right? Sorry. Cosine v, right? That's this piece. Times, now, the partial of y with respect to v. So what is the derivative of this thing with respect to v?
Negative u cosine v.
Careful, I think you're antiderivating.
Oh, U cosine.
Yeah, so u is going to come for the ride, because u is a constant this time. Derivative of sine of v is cosine v, right? So we're going to have u cosine v. And then we have minus, now the partial of x with respect to v. So what's the partial of this with respect to v? So negative will come out this time, u sine v. So negative u sine v. And then times now this piece. Partial of y with respect to u. Just sine v. Okay, we want the absolute value of this. Do y'all see what happens? This is u cosine squared v, right? Plus u sine squared v. And so when you factor u out of each of these, you got the Pythagorean identity right there, right? So this is just that, right? So you get this, right? That's what needs to be inserted into the integral every single time. If you ever want to change your variables from x and y to this, then you must include in your integral that computation, which for us in this particular change of variables is just u, which over here is really r, right? That's what r was before, right? The r is like the u here. So do you see now why in polar you have to put an r there? It's because of this. Now I haven't shown you why you have to do this. I'm just telling you the formula first. I'm going to try and convince you of the formula next class, but it's difficult to do. It's difficult to convince you of the formula. Is that all right? So what happens if you want to do a triple integral over e of f of x, y, z with respect to volume, and you want to make a change of variables? Well, I don't have it here. What happened to my notes? It's okay. I'll show that to you next time. I told you 10 minutes. It's been 10 minutes. I think that's a good place to stop. You have 2 sections we covered today, and no, it's only like 5 or 6 problems of homework. Just make sure you can do them. Next time we meet, you're supposed to turn in a take-home, if you're doing it, but we're running out of time to do take-homes. I have had a few calls on the take-home, and some of those problems are, going to require some thinking. All right, everyone have a great day. I think we're done, yeah? You feel done? Yeah, so that's a super interesting